Hi guys, today we're going to be doing the Unit 8 Area and Solids preview video, 8.8, Solids and Similarity.
All righty, friends, let's breathe. Ready, inhale. Deep breath, hold for 3. And exhale. 2 more times, ready, inhale. Hold for 3. And exhale. 1 more time, ready, inhale. Hold for 3. And exhale. Last video of the year, we have a couple guests.
What's up? Miss Way wanted us to come on and tell you what you'll be missing. Miss Way is an awesome teacher. She will help you when you need help, even though you don't know that you need it. Guys, Miss Way will help you with algebra too. Go to Miss Way during lunch. Very good.
Even though I never had Miss Way as a teacher, you know, you can come to understand the level of excitement and joy she brings to geometry of all things, okay? It's geometry. And, you know, every time, you know, you see her working relentlessly on assisting her students, and it's just encouraging to see how much passion you have for what is often is a thankless, sometimes thankless job. So this is during Teacher Appreciation Weeks. Say thank you to Miss Way. Go do that. It's probably a good idea. Also, that steak that she made looked really delicious. I'm kind of jealous. Keegan, you almost got over the keyboard. Senor Keegan.
All righty, friends, let's get to business.
Bye, Miss Way.
Bye. I got to
Preview similarity. Don't forget date, time, and location. And yes. All right, we're going to do a quick shout back, way back. This is in December, early December. We talked about S.C.A.R.E. S.C.A.R.E. So taking a look here, remember S.C.A.R.E. What does S.C.A.R.E. mean? It means similarity means similarity. Similar means congruent angles, ratios equal. S.C.A.R.E. S.C.A.R.E. Congruent angles, ratios which are equal. The slang definition of S.C.A.R.E. is solids, similar solids which have the same shape but a different size. We're going to check the following solids to see if they are similar by seeing if the ratios are equal. So in S.C.A.R.E., S.C.A.R.E., we're going to check for similarity, checking for equal ratios. And we're working left to right. So working left to right here, 3, 15. That reduces 1, 2, 5. Let's check 8 and 40. Also 1 to 5. 5 and 25. Also 1 to 5. So that makes these first prisms similar. Why? The angles are congruent, they're right angles, and the ratios are 1 to 5 on all edges. Let's check this one. 9 to 12. 3 goes in here 3 times. 3 goes in here 4 times. 9 to 12 again. 3 goes 3. 3 goes 4. And then 15, 25. 5 goes in here 3 times. 5 goes in here 5 times. Whoops. 3, 4, 3, 4, 3, 5. These are not similar. So I would like you to take 30 seconds and determine whether or not these cones are similar. 30 seconds. Use the same, checking for ratios which are equal. Thirty seconds, go. Let's check. So you have to make sure you're tracing the same thing. So 20 to 100, 20 goes in there once and 20 goes in there 5. And then here, the radius here is 10. And the radius here, if you did 100, you would say they're not similar, but you're going from radius to radius, which means 10 to 50, which also reduces 1 to 5. This was a yes, they were similar. So you have to make sure you physically trace every single segment. Same shape, different size is the essential definition of similarity. Same shape, different size, because all spheres have the essential same shape, just different size. All spheres are automatically similar. Automatically similar. You don't have to check ratios because they are already the same shape, but just a different size. Now, before we go on to our next phase, let's recap the concept of dimensions. If something just has length, like a car driving, and it drives 50 miles, that concept of 50 miles, driving 50 miles, is a one-dimensional concept. It's just length. Two-dimension would be like paper. What is the area of this paper? That is something that has both length and width. The concept of area has length and width, 2 dimensions. Something that has both length, width, and height. That's 3 dimensions, which we know as volume. 1 dimension is length, 2 dimensions, painting a wall, area, 3 dimensions, volume, 3D. Box that, star that, smiley face that. Whatever it is, you need to remember. Repeat after me, nice and loud. When you change dimensions, you change ratios. When you change dimensions, you change ratios. When you change dimensions, you change ratios. So when you were in, let's say, 2nd grade, maybe 1st grade, who knows? You learned this ratio. 1 yard is 3 feet, but you were lied to. Not exactly lied to. I'm using that euphemistically. You weren't given the entire truth. Because 1 yard is 3 feet is only true when you're in the 1st dimension. 3 feet is 1 yard. 1 yard. So in the 1st dimension, you have a 1:3 ratio. 2 dimensions, shade this. Now we're dealing with area. Area, this is 1 yard. This is 1 yard, which means it is 3 feet here. 3 feet here, you're following along. Done this in class several times, which means a yard squared is 1, 2, 3, 4, 5, 6, 7, 8, 9 feet squared. So the ratio in the second dimension is 1:9. Volume. Volume is 3 dimensions. So if I have a yard cubed, this is a yard, 1 yard, this is a yard, 1 yard, and then a yard depth, 1 yard. So volume of a prism is base times height. So if I were to draw this and shade it, that would be a square yard, which is 9 feet squared. And then we go depth-wise or height-wise, 3 feet up. So that's going to be 9 times 9 times 9. If this was all turned into nothing but cubes, think of it as sugar cubes, that would be 27 feet cubed. 1, 2, 27. When you change dimensions, you change ratios. Watch very carefully what I write. The exponents correspond to the dimensions. So if our ratio is 1:3 in the first dimension, that's like saying 1 to the first, 3 to the first, which is 1:3. Second dimension, that's 1 to the second power, 3 to the second power, which changes 1 to 9. Third dimension, 1 to the third power, 3 to the third power, which is 1 to 27. So exponents follow the dimensions. Exponents follow the dimensions. What does this look like in a real life problem? Now, here's what I want you to visualize is you have a cube and you take the cube, the edge length, and now I simply want you to double the edge length, double that edge length compared to this. This is 1 bunny hop, 2 bunny hop. 1 edge length and double it. Now, I would like you to write down, just take a wild guess. In this scenario, if I were to take a cube and I were to take its edge length and double it all the way around, what do you think would happen to the area? What do you think would happen to the volume? Estimate. I'm going to give you 20 seconds. I expect you to write that down yourself. Let's actually do an example and see what happens. Let's say the edge length starts at 3 centimeters and it's a cube, so it's 3 centimeters all the way around. So if we double, our edge length becomes 6. Scale factor, ratio of the sides simplified. Ratio of the sides simplified. So our scale factor is going to be 3 to 6 and then reduce it. Reduce it, and that's going to be a 1:2 ratio. So at this moment, our 1D scale factor is 1:2. Now imagine if you were to lay out flat, unpeel this cube, and find its surface area. In other words, how much paper is involved. So here, if this edge length is 3, let's just do one of each of these. That edge length is 3. That means that edge length is 3. That means the area of each square is 3 times 3. It's 9. Well, technically unit squared. We'll just not rewrite it all. 9. So let's find our area. 1, 2, 3, 4, 5, 6. So 6 times 9, it's 54. Check units. Yep. 54 centimeters squared is the surface area of those cubes. Over here, each edge length is going to be 6. 6 times 6, that means the area of each cube is 36. So 36, 36, 36, 36, 36, 36. So 1, 2, 3, 4, 5, 6 times 36. $216 centimeters squared. Keep that in mind. So that's the surface area. And then the volume of the cubes, base times height, or because they're cubes, length times width times height, which in this case, our volume is basically going to be 3 times 3 times 3 again. So that's 27 cm cubed. And this one is going to be 6 times 6, 36 times 6 again. And we get 216 cm cubed. Now, there is a pattern going on here. There is a pattern going on here. Watch very carefully. Our scale factor, okay, originally we had 3 to 6, which reduces to 1 to 2. In 2D, we had 54 to 216 centimeters squared. So 54, 216. We're going to reduce until we go all the way down. 54 goes into 216 4 times. So this is a 1 to 4 ratio. In 3D, we have 27 to 216. And that's going to go into there 8 times. 27 goes in there 8 times. So we have a 1 to 8. Watch very carefully. 1 to the first power, 2 to the first power. 1 to the second power, 2 to the second power. 1 to the third power, 2 to the third power. 1 to the first power is 1 to 2. 1 squared to 2 squared, 1 to 4. 1 cubed, 2 cubed, 1 to 8. When you change dimensions, you change ratios. So here's the generic version. Whatever you start with x to y, that's your scale factor to the first power. The ratio of your area is going to be x squared, y squared. The ratio of your volume is going to be x cubed, y cubed. When you change dimensions, you change ratios. We're going to do 4 problems together. 2 together, 2 on your own, and check. Put your finger on the paper, finger, out loud, read. Underline your keywords. That's a ratio volume. Right above the word volume, put 3D. Diameter, smaller sphere, 12 cm. So here's our smaller sphere. Our diameter is 12 cm. What is the volume of the larger sphere? Volume. So to get the volume, we need both the diameter and then, of course, the radius, because all you need to find the volume of any sphere is ultimately the radius. When you're working with changing in dimensions, always do all 3-dimensional ratios. So right here, we are already given the ratios. That's not the actual volume. The ratios, 27:8. But that's in the 3D. So keep in mind, technically that's x cubed, y cubed. Your job is to backtrack. What are the ratios going backwards? This is how you think of it. X cubed is 27, y cubed is 8. What number times itself 3 times gets you 27? What number times itself 3 times gets you 8? 27, that answer would be 3. For 8, the answer is 2. So your one-dimensional scale factor is going to be 3:2. And then if you're in the second dimension, you square it. So 3 squared is 9. And then 2 times 2 is 4. So now I have all 3 ratios to work with. And the question is, I want to find the actual diameter here. So you ask yourself, this diameter, is that 1D, 2D, or 3D? Since it's just length, we are working in the one-dimensional ratio. Our one-dimensional ratio is the 3:2. So I'm going to use 3:2. And I always like to label my ratios. This is the larger sphere to the smaller sphere equals larger sphere diameter. I don't know. Smaller sphere diameter is 12. Cross multiply, solve. So I just found my diameter of our larger sphere is 18 cm, which means my radius is going to be 9 cm. What's your actual question? Find the volume of the larger sphere. Volume 4 pi r cubed over 3. 4 pi, that's 9 times 9 times 9 over 3. Going to take the 3 in one of those 9s. And if you see here, I basically have 12 times 81. And my volume is 972 pi form, pi, check for units, cm cubed. So you find all 3 ratios, first dimension, second dimension, third dimension. Then you ask yourself, which one do I want to use? Finger on paper. Right there, ready, read. We are told that these are similar. Now we're not given all the dimensions. Now, if I just wanted you to find volume, if you knew the length, the width, and the height, you just calculate it, but I don't give that to you. Instead, what I give you is simply one edge length, corresponding edge length, and then the actual volume of the larger prism, and your job is to find the actual volume here. Now, because they are similar, you start with the scale factor. Ratio of the sides, simplify. Sides simplified. So 12 and 8, 4 goes in there 2 times, goes in there 3 times. So left to right, it is a 3:2 one-dimensional ratio. My two-dimensional ratio is going to be 3 squared and 2 squared, which is 9 and 4. My third dimensional ratio is 3 cubed, 2 cubed, which is 27 and 8. You should have your cubes memorized through at least 10. Now, look at what we have. Start with what we have, not with what we need. We have the volume of the larger. We have the actual volume of the larger, which is 1,944 inches cubed. We are not going to use the 3:2 ratio. That's only one dimension. We're not going to use 9:4. That's 2 dimensions. Volume is 3 dimensions. We must use this ratio, 27:8. The volume of the smaller is X. Match your dimensions with your ratios. Cross multiply. I have 8 times 1,944 equals 27 times X. So, of course, I'm going to divide by 27. I know 9 goes in here 3 times. I'm going to go 1,944 and see if 9 goes in there directly. 4 plus 4 is 8. 8 plus 9 is 17, plus 1 is 18. So I know that adds up to 18. So I know 9 goes in there. So 9 goes into 19 twice. 9 goes in there once. And 6. So I cross that out. That's a 3. This is a 2, 1, 6. And now I see, does 3 go into 2, 1, 6? I'm going to add 6 plus 1 is 7, plus 2, that makes it 9, which means 3 does go into directly. 3, that's 7 and 2. So cross it out. 72. 8 times 72. 16, carry the 1. 56, 57. So the volume of the smaller is going to be 576 inches cubed. We'll do one more with you, and this last one, you're going to try on your own. Said below are 2 similar square-based pyramids. So these are squares down below. The volume ratio is 8 to 27. The base of each pyramid square, the base of each pyramid is a square, and X equals 6 right there. You're going to answer the questions below. So step number 1, we're given the volume ratio. So that's 8 to 27. So keep in mind that is X squared, X cubed, Y cubed. So what number times itself 3 times? That means my scale factor is 2 to 3. And the area of my ratios is going to be 4 to 9. Now we're going to find the variables h and y. Height. And find the height here. We have the height here. I want to find the height here. So I use height to height is a length issue. So 8 to h is going to be the same, smaller to larger, as 2 to 3. Cross multiply. H times 2 equals 8 times 3 divided by 2. So our height is 12. Height is 12. Now we need y because we want to find the volume. So left to right, I have y to 6. Again, first dimension because it's only length, 2 to 3. So I have 3y, 6 times 2. Equals 4. Now we can find the volume. Volume equals base times height over 3. So here our base, 4 times 4, 16. Our height is 8 over 3. Here our base is 6 times 6, so it's 36 times our height, 12 over 3. Reduce if at all possible, and it's not, so 16 times 8. So my volume here on the left is going to be 128 units cubed. Volume on the right (36 times 4) and 44. So we get here our volume is 144 units cubed. This page I want you to do on your own. Pause the video. Welcome back. Let's see how you did. You should be correcting with red pen, folks. Last one, don't get lazy. Get out your red pen. Should be red pen markers. If you get it correct, star smiley. If you get something wrong, totally fine, as long as you write a note. Our scale factors one dimension is 3 to 4. Volume of the solid, and it's smaller solid. It doesn't tell you what the solid looks like. So I'm simply going to draw a couple cylinders here. And this volume of the smaller is 108 meters cubed. Volume of the larger, we don't know. Our surface area is going to be 9 and 16. Our volume, 3 times 3 times 3 is 27. And then 4 times 4 times 4 again is 64. Ratio. Smaller, larger. 108. Unknown. Have to use the third dimensional ratio, 27, 64. Cross multiply. Key to multiplying is not to multiply. It's to factor. You're asking yourself what goes in each. So I know 3 and 9 goes into 27. So 3, let's do 3 first. 3 goes in here 9 times. And 3 goes in here. Nope, it's not 108. 3 goes over here. 3 goes in here 36 times. And then 9 goes into 36 4 times. So 4 times 64 is 216. So your actual volume here is 216 meters cubed. When you change dimensions, you change ratios. This one also, you do on your own. Pause the video. Welcome back. Let's see what you did here. Your ratio of your surface area. You're now in the 2-dimension. So you backtrack to the first dimension. Square root of 25 is 5. Square root of 16 is 4. And then go forward. 5 times 5 times 5 is 125. 4 times 4 times 4 is 64. There we go. It says here, what is the scale factor? We just did that. Find the variable h. H is only 1 dimension. So h over 24. This is large to small equals 1 dimension, 5 to 4. Cross multiply. 4 times h. 24 times 5. Divide by 4. And your h is going to be 30. Check units. It's just units, whatever they are. There we go. When you change dimensions, you change ratios. Summarize this last video note of the year.